Hello, this short video should help you on this homework problem. This homework problem has 3 parts. Let's take a look at them. All right, so we have the first not part B, part A right here. All right, so I just want to highlight them so you can see them within all of the other informational text, which mostly is all there to spell out the formulas that you need to use. That's the purpose of all the extra wording, okay? And also telling you what units to report your answers in. So there's no ambiguity and question about that. There we go. Okay, so those are our parts A, B, and C. Now we're going to write right on the side the equations that we're going to use. Make sure I have this nice and out of the way. So for part A, we're going to use the equation for finding weight when you know the gravitational acceleration on the surface of some world. You know the local gravitational acceleration. It varies between planets. It doesn't vary much on a planet, and it also varies based on elevation, which is the distance from the center of the planet. So you might have a few tens of centimeters a second squared difference when you go a couple 100 kilometers further from the center of the planet that you're currently on. But that's, I guess, a little tangential. Let's get back to actually using the formula right here. Weight equals mass times gravitational acceleration. That is the one and only formula to use for part A. Okay. Now B also has its one formula, and that one is a formula that we use when we know the mass of a world, the radius of a world, and we know the value of the universal constant of gravitation. Okay. And so let's use our trusty highlighter again to take a look at the value for universal gravitation right here with the units cut between the lines, okay? And then we're going to enter a person's mass because we actually do want to get a value of newtons out of this, I believe. So let's see, or do we want a ratio? So if the same person on a different planet had a mass 3 times, oh, okay, no, we're going to use the same mass that's given up here, so we're going to carry that value over. So when we had the value of mass right here, little m, for the formula for part A, we're going to use that same little m for the formula for part B, which I'll write down in just a second after I take note of our last step here when we're discussing collecting our variables. No more constants, but we do have our little m. We have our mass of the planet or moon, and we have the radius of the planet or the moon. All right. And when you have all that information, you can actually calculate g, okay? But in this case, we're going to use it to calculate w because we're going to put m right in the formula already, okay? But if you do eliminate m from this formula, then what you're left with are the exact values to actually calculate g itself if you are not given it. So you have 2 types of presentations of information. We're actually given the gravitational acceleration. Maybe it was directly measured. There's a number of simple experiments you can actually do to measure gravity pretty easily, as well as, of course, any kind of accelerometer in a digital device. But then, we know it on Earth to be 9.80 meters per second squared. Here we are told that on Mars, and this is a realistic number, that it's 3.72 meters per second squared, okay? We also have a realistic number for I think we do, oh no, this is just imaginary planet here, that is 3 times Earth's mass, but the radius is only twice as big. So I guess it's a denser planet than ours, all right? And then finally for the last part, I should actually write down the formula over here. So the one and only formula we use for part B is going to be, I should write this from the beginning. We're solving for weight again, just like in part A. We're using a different formula to do so because of different information. All right. You can also think of this as more fundamental information, really calculating the source of the gravity rather than just its manifestation, right? Because the gravitational acceleration is a cause, not or rather it's an effect, not the cause, right? It's not the source. It's just something that happens as a side effect. All right. So moving on to our last part, part C. All right. And then we just want to put down the one formula to use here. All right. And actually this last paragraph is not for this problem at all. So let's go ahead and cross that out. This is going to be sort of lead up information and values that we'll collect for part B, question 2, which will have its own video. All right. So then For part C, we now have, or we're now asked, how much would the same person weigh in newtons on a small moon that has a radius, and so on. Okay, so for part C, we're actually just going to use the same formula again. So big G, M, and R squared, okay? And really no significant difference there. There are sometimes you can do a shortcut in the approach if you find the weight on one planet and you're given an imaginary planet that's some even multiples in terms of its mass and radius, like part B, then often you actually don't have to put in all of these big scientific notation, particular values. You can just figure out how much heavier you are on that other world because of those even integer multiple increases in values, and essentially you have your new weight over your old weight. And it saves you a little bit of calculator entry, but that's actually not the way I ended up writing this. So it's going to be sort of calculator entry the whole way, with the only difference being a thematic difference between parts B and C, because one is some imaginary denser world that's comparable to Earth, and the other is an actual moon, right? It's the how much will the person weigh in newtons on a small moon? No, it's not an actual moon. For some reason, I kept thinking it was the moon Iapetus, but it's not. Okay, which is a moon of Saturn, I believe, Iapetus. But I suppose it could be any number of interesting moons out there in the Jovian systems around the big gas giants. Okay, so let's go ahead and do a example calculation, but not with the values that you were given, but instead with some different values. Okay, so I'm just going to go ahead and cross out the original values and write in the new values that I want to use. Okay, so let's take a look. Let's go ahead and use, instead of 85 kilograms, we're going to use 71. All right. And then let's think of a world that is not 3 times Earth's mass, but instead is going to be 8 times Earth's mass right there. So 8 times bigger, and has a radius that, instead of being not as big as you would expect, is instead going to be overcompensated in a sense. So let's have it, instead of being twice as big, we'll have the radius go up by a factor of 12. All right. So this is more of a gas giant, but sort of some terrestrial version of it. There are things like super Earths and denser planets. There actually are planets that have water in more of a liquid state rather than a gaseous state, but almost the size of a gas giant. So we'll imagine it's one of these exotic planets that astronomers have discovered around other stars. Okay, so those are going to be our values, and those values will be multiplied by something I haven't really called our attention to, but by the given values for the mass of Earth. All right, I'm missing an H there, and the radius of Earth. Okay, notice these are both given in base units, so you do not have to worry about any conversions. All right, so I made our lives a little bit easier there. The gravitational constant you will always see in base units, certainly in this class or in any college astronomy class. Okay. All right, and then we're going to consider our moon. By the way, there is one thing that's interesting here. Part B, we had, as I just said, everything was given in base units, everything being mass and radius, right? So both values. But the radius in part C is not given conveniently in meters, but in kilometers, so it needs to be converted. In other words, 880 kilometers is 880,000 meters, right? So you multiply it by 10 to the third, or 1,000. Our mass, though, is given in scientific notation, which generally means it's going to be given in kilograms, right? Rather than using the metric prefix way of denoting things, like with a K, right, for 1,000 or kilo. All right, but still same formula as we talked about for this one. And the only thing I want to do is change the values there. By the way, I'm not going to change the values of Earth and Earth's mass and radius. Let's stick with the real numbers there. But let's have our imaginary moon be a bit different here. So we'll have it be, if we make them quite small, sometimes we can have quite a bit of microgravity, which is true. There are tons of moons out there that if you were to walk around on them, you'd be so light, maybe 20 times lighter than here on Earth. So it would be truly microgravity in a strange world indeed. Okay, so let's have, so our radius here is going to be 700 instead of 800, just 700 even. Still stick with the kilometers, and I'll just note right here, because I'm going to do this anyway, change it over to 700,000 meters, so 700 times 10 to the 5. Hopefully that's legible. And then here for our mass, cross this out, put our new mass over here. So our new mass we're going to have for this moon kind of the right scale here, but I'm going to make it go right down to the next order of magnitude. So in other words, 10 times smaller, or at least, a factor of 10 smaller, right? So, but on the high end, right? Because 8, of course, is bigger than 4. And we'll have 10 to the 19 and kilograms. All right, so we're all set. Let's go ahead and run the numbers. To do that, I'm going to get Desmos up and running, which I thought I had here on the bar, but I don't. But luckily, we can easily navigate to and just seamlessly get this all started. Well, maybe not seamlessly, but there we go. All right. So first calculation, part A with our new values, and we'll wrap this video up. Okay. So taking a look at part A, we have our calculation, which is going to be plugging in just mass times gravity. So we'll use our 71 kilograms. So we're solving for weight here, W for weight. So 71 kilograms, okay, then multiplied by some gravitational acceleration, which, that's one number I forgot to scratch and change. Let's use, I don't know a real one off the top of my head. So, let's see, the moon is always said to be a sixth of Earth's gravity. So whatever, we'll just write this down as a fraction. I'll say the moon, okay, and it's going to be written like this. So 9.8. Make that look more like division. 9.8, all right, and then over 6, and then we'll just have our meters per second squared, okay? We'll see what that is as a decimal in just a moment. All right, so that's going to be, let's see if we have our value. I'm going to call this G, all right? It's, I'll go ahead and give it a subscript, and we'll call it, like as we said, M for moon. Okay, but I don't think I'll be using that letter again in this calculation, so I could have just left it without a subscript. But regardless, let's plug it in. So it's going to be 9.8. And this way I'm giving it a letter and I'm writing it like this, like an equation, just for one reason and one reason alone, so that Desmos saves the value so that I can just do a calculation later and just refer back to that letter, don't have to type it again, and I don't have to worry about any rounding errors. Okay, so divided by 6. There is our value of gravitational acceleration, pretty close to reality of what you'd find on our moon, right, on Luna. And so we have 1.63 meters per second squared, just like that. All right, so now let's plug the whole process in, or both numbers. I'm also going to define my mass, which we'll use a couple of times, as I talked about, right, because we're going to use it, I think, because it says how much would the same person, right? So this person's traveling all over the place. They start on, in our solar system, and they go to a couple of exotic worlds in other solar systems, and their weight changes as they go, okay? So M is our first step here, and, just writing the letter, and then we're going to define it as 71, the number we chose for our mass, all right? And it's kind of a typical human being size. Okay, so sure enough, our weight, and I'm going to call this just subscript A, just to tell us and tell myself that it is for part A, our first value, our first stop on our intergalactic journey. So we got our G with our subscript of M, and you can actually define uppercase subscripts. They would be separate. So if I had call that G, if the denoted subscript of uppercase M, it could save it as a different number, and Desmos would distinguish between the two. All right, and then our just little m, no subscript because there's only one m. We'll use it throughout the whole system, right? All right, so then we're going to use 3 significant figures, which is written throughout the problem. All right, so just stick with 3 here, and that's true of basically all the problems that you'll solve in this class. And that just means, keep 3 numbers throughout the rest, if you're not familiar with the term significant figures. And you got to make sure you follow the rounding rules here. And so we have 115, right? But, I'm not just going to write 115 because I'm told to just keep 3 numbers. I have to look at the next number is, in this case, is a 9, right? So it's very close to, the next, honestly, 116. So we have to round up to 116, okay? So it's 116. And, throughout the body of the problem, it does say to give your answer in newtons. And that's because that is the metric unit of force, and a weight is a force, so that's why we want to give it in newtons, okay? In the imperial system that we use in America, our unit of force is the pound, okay? But in the metric system, it's the newton. There we go, all right? And all forces are, can be thought of in the context of Newton's second law as a mass times an acceleration. In this case, a mass times a gravitational acceleration. All right, on to part B. Okay, this is the first time we're going to use our formula. which is known as the law of universal gravitation, okay? And we're going to solve for weight again, okay? A lot of times when you see this formula, you might see it with an F on the left-hand side, so you might see something like this, F equals G, little m times big M over radius squared, or sometimes it's two big M's multiplied together up there in the numerator because maybe it's the gravitational force between two worlds, right? So maybe the tug between planets, right? Well, but it's usually little m if it's something small like a satellite or a person, okay? Whether it's a satellite in motion or just a person right at rest on the surface, So all that considered, it's often an F because we think of it as gravitational force. But, again, weight is a force and our focus here is on weight. So we're using W for weight. All right, so then let's put in what the formula looks like. So we have m r squared, just what I just wrote, but it's run to the right a bit neater. And now let's plug in all our values, okay? So the first one, this is always a constant. You want to have it on a formula sheet. You want to not worry about memorizing it, but just always have it handy. I use it enough that I do have it memorized, 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. And actually, if you just memorize the formula, you also memorize the units because you know that G is going to have to work out with kilograms squared up in the numerator, right? So right here, kilograms squared in the numerator and meters squared in the denominator to give you something that is just going to be newtons, and that's exactly what this shows, right? It's just newtons and then the two things that need to cancel. So we have newtons on both sides of the equation because every equation in physics, every equation in astronomy has to not only be numerically true, right? So numerically equal on both sides of the equal sign, it also has to be dimensionally equal on both sides of the equal sign, which just means that it has to have the same units on both sides. All right, so in this case, newtons on both sides. So then let's have our fraction. So we have the product of masses up top, just the 71 kilograms. All right, so our little person compared to our giant world, and our world in this case particularly big, 8 times bigger than Earth, but Earth is no tiny thing itself, right? So we have 8 and then times the incredible mass 5.972 times 10 to the 24, and yes, this one has 4 numbers in it rather than 3. But since most things don't, that's why we keep only 3 in our answer. If you were wondering about significant figures, otherwise don't worry about it. And just remember, always give me 3 numbers and round. Okay, so there we have everything that goes up in the numerator. And down below, we're just going to put in our radius, which is what is going to be 12 times Earth's radius. So just 12 times 6.74? 6.37. All right, and then times 10 to the 6. So 6.37 million meters, which is to say that it's 6,370 kilometers. All right, but here we have it in meters. And the big thing that you got to remember is you have to square this number, okay? In this case, because since it's 12, the 12 goes in there because that's just the radius of this world. You have to square the whole thing, okay? It's the biggest mistake I see, just people forget to square it. Maybe they know to, but I'm just reminding you, make sure, double check your work, that you have remembered to square the radius down in the denominator. It makes a huge difference with your number. Trust me, it does, okay? So let's go ahead and calculate this, and then we'll have our number for part B and be right on the C, which is just rinse and repeat, really, okay? So as far as comparing to part B, A is obviously distinct. Okay, so let's go ahead and define our universal constant of gravity, big G, right? Because as always, little g is just like world specific, right? On Earth is 9.80, and that's important to us because all of humanity lives on Earth, but there's a lot of other worlds out there. So other aliens, they have their own G, right? But big G should be the same anywhere. We can go to a different galaxy, and it's always going to be big G. It's somehow set by the tuning of the universe itself since the Big Bang. So some sort of fundamental thing, right? We don't know where it comes from. We just know that it applies universally. Okay, how do we know it applies universally? Because of the types of observations that astronomers make. Okay, when they look at the dance of stars or the way galaxies interact with each other, tug on each other, crash into each other. So 6.67 times 10, and then to the almost negative 11, right? So it's a very small number, right? Gravitational constant is a very, very small number. When you have a lot of mass, it ends up being a strong force. Okay, so there we have that. Okay, and then we already defined little m, so now we're going to find big M, and this one will have a subscript of part B because we're only using it in part B. We'll have a different big M in part C. And the one that we're going to use is, these are actually just the Earth ones, and we'll multiply by a, you'll see like when we get to it, okay? So we're just actually going to define it for Earth. So this would be actually the same, if you're going to be using Desmos, this would be the same constant that you should put in because I'm going to multiply it by 8. You're just going to multiply it by 3, right? So that's the only difference. We just put the multiple, the integer just right into the formula. So it's kind of, here, I'll highlight where I did it, or maybe change the color. So, like, I'm going to define, that constant, but then right here, I'll just put my integer. Okay, so let's make this. All right, so this is the only thing that's actually going to vary between, my version and the original. So color right here, and there we go. Okay, so continuing on, let's put the actual mass of Earth. So 5.972. How do they measure the mass of Earth? They just put Earth on a scale. Just do a giant scale, no problem there. Obviously, that's not how they do it. All right, 24, okay. And then the radius, 6.37 times 10 to the 6th. All right, all good there. Now let's finally put it all together, because we're actually ready, except I need to actually define this as R. Missed a little step there, important step, right? So big R, and I could actually just leave it as big R, because we're not gonna. We could then define one part C with a subscript, but I'll just keep being detailed here and have our. I want a subscript. Okay. Oh, that's right. I have to get out of that mode, and we're going to use capital E again, because Earth, capitalized. So I was in the habit of doing that. And get out of the subscript, equal sign. Okay. A lot easier to do it on the keyboard, but works okay on the iPad as far as using Desmos. Okay, there we go. Now I'll write all those numbers in and then put it in the calculator. All right, that's the way we've been doing it, so I'll do it here as well. So get down here, and we're going to have in parentheses. Actually, no, I already did it here. We're good. We can do the final step, because we already wrote out all the numbers. Okay, so now let's just have it. This is going to be weight, and then subscript with part B. Okay, and then equals big G. Okay, and then we'll start our fraction right here. So let's have, I'm just going to put in one of the numbers, just M, and then I will do, actually, I want to have it look like it, just because I'm picky like that. So we'll put a multiplication symbol and then do division, so that it's going to look just like the formula is written. Essentially, I want what is, symbolically showing up on Desmos. Symbolically just means like using the variables that I've defined, like, R sub E, right, subscript E, and just make it look like that, okay? So then we have up in the numerator, uppercase M, but it's Earth's mass, so we defined it as a subscript there, okay? And then we'll just put in our radius, okay? And we'll give it its appropriate subscript also for Earth, okay? And then we'll put in our multiples, because we're in a world that is 12 times bigger, so we'll put the 12 there. We won't forget to square anything, and remember, we have to put the parentheses around both the, what we're multiplying R by and R itself. So we're squaring the whole thing. Okay, there we go. Close the parentheses and square it. Okay, and then up top, we're good except for the multiple, because we want it to be 8 times Earth's mass. So just put 8 right there. Oh, not the subscript. I don't even know why I was in a subscript. There we go. Just put 8 right there. I see. That's weird. Okay, so let's just do a multiple symbol and an 8. There we go. Right? It wanted to treat it, by default as a subscript. Wow, we got it. Okay, so we have a mass of 30. Not a mass. No, that's a big mistake for me to make. We have a weight of 38.7 newtons. All right, and you know what? Here, I'll put some boxes around our answers a little bit. Okay, that's a terrible box. All right, so in the first one, that was our answer. So let's put that in. Yeah, I cannot draw this box. Okay, last time. All right, good enough. Okay, and then for this one, for the 38.7 for part B, right? Because of course we are just finishing part B here. All right, very good. Okay, now what's interesting is we can see that on the moon you're already pretty light, right? On Earth you'd be 6 times heavier than this, because 6 times the gravitational acceleration, 6 times the weight, right? And the whole idea is I used 9.8, our gravitational acceleration divided by 6 to get this number here, the 1.63. So this is already pretty light, but the world that we came up with a mass that, is a lot bigger than Earth, and the more mass, the more gravity, but it's so much bigger also in size that you're further out, everything's dispersed more, and means you're really light. So this would be a very microgravity type of world, right? So you'd be kind of like almost not, floating around, but you feel light as a feather, okay? And then finally, we'll just do it for our last set of values here, and we'll just plug them in. And the whole idea here, just to be clear, is this one, you don't have the multiples, you're just using the given values. All right, so just these ones, okay? All right, and I haven't really been putting in subscripts here. I just been, replicating the formula, and then obviously I called attention over here. So we'll just do the same in this one, but we'll put in our values. And it's not equals equals, so we have multiplication there. So we have our 6.67 times 10 to the negative 11 Newton square meters over square kilograms. And then we'll multiply by the 71 again, but then we're going to have 8.11. So 71 times 8.11 times 10 to the 19. This is going to give us another really small acceleration. Actually, this one's going to be much smaller. Although I keep saying it's acceleration because sometimes I solve for that. Here we're solving for the weight, so everything's in comparison of weight. So you think about how much lighter you are, right? So obviously you're a lot lighter on this imaginary world than you are on the moon, right? As I was just saying. And then we'll take our 700 kilometers, which is just going to be 7.00 times 10 to the 5, because it's 700,000. All right, and that's going to be in meters, almost 4 kilometers. And don't forget to square it. There we go. That's what we'll go ahead and put in the calculator. And I won't even bother to define all the variables this time, just to show you that you don't always have to do that. So just put equals, we'll use G since it already is defined, for that matter, actually we'll also use M, but then that's where using the values will stop. Again, I'm going to do the division first, so it kind of like sets it up in the right way, but then I'll go back up to the numerator and multiply just by 8.11 times 10 raised to the 19th power. All right, there we go. And then down here, open parentheses, so I don't have to square it, 7.0, right? Don't bother double zero, times 10 to the 5th, close those parentheses, and square the whole thing. All right, so now we have, talk about microgravity. On this little world, we would only weigh 0.784. Again, remember 3 numbers, and you got to round, right? And so the 8 means 3 rounds to 4. Wow, so we weigh less than an apple, because people always say, oh, an apple is around a Newton, right? I mean, I guess that's a pretty big apple, right? Because Newton's about 1.5 pounds, or let's see. Actually, I'm not sure exactly how. I can't think of it off the top of my head. Newton. Well, if you weigh 100 pounds, if you weigh 150 pounds, then you have about 770 or 650 newtons. So there's less newtons per pound. So you actually divide by it, so that by quite a bit, right? So a Newton, okay, yeah. So Newton is maybe like 1/4 of a pound. Okay, so yeah, about 1/4 pound for an apple, for a big apple. All right. So, but here we're even less than that, right? So we're just a few ounces, right? So we would just weigh a few ounces. Okay, so there you go. There is an example of calculations. Depending on a lot of lightweight ones, we didn't go to any worlds where we're heavier. You could go to worlds where you're actually heavier, but none of the numbers worked out that way. The numbers that I chose. But in yours, you should have at least one where you are heavier. I think part B with the original values, you should get a weight that's more than it would be on Earth, and certainly more than it would be on Mars. All right, because you're already lighter on Mars. Not as light as you would be on the moon, but lighter than Earth. Okay? But all that aside, I hope you see how the math works, how the calculations work, how to read the numbers, make sense of the values, and I hope you found this homework help video helpful. Bye for now.